Hello everyone, welcome to EEEE Lab number 7. Today we are going to discuss the power factor improvement circuit. So, the aim of today's experiment is to improve the power factor of a single phase inductive AC circuit using a capacitor across the load. A load is RL load. Okay, so let us understand the concept of a power factor and why we require improvement of it. So, the concept is like this. Let's say you have an electric AC motor. Now we know that electric AC motor converts electrical energy to mechanical energy. Now it converts electrical energy into two forms, namely mechanical energy in the form of rotary motion and magnetic energy. So basically, if we see, magnetic energy is a kind of a waste because we want to convert electrical to mechanical energy. But without magnetic energy, your motor will not run. So, such form of energy is called as reactive power. Note, reactive power must be less as possible so that the load will utilize maximum power and the current requirement will be less for the same amount of power. So basically what we are saying is the magnetic energy is necessary, without which the functioning of the motor will not be proper, but we have to reduce it. It has to be as less as possible. Okay, so the bottom line is to reduce the reactive power of the circuit, different power factor improvement methods are used. Okay, so we will have a more clarity over the power factor improvement in short time. Let us understand first of all what is a power triangle. Okay, so this is a power triangle. Your this is my active power or true power or real power measured in watts, and it's denoted by capital P. This tangent over here is my apparent power. This is the unit is V into A and is denoted by capital S. And this height over here is my reactive power, which I want to reduce, which is Q, which is measured in VAR. Fine. So over here, the power factor is given by true power divided by the apparent power. In terms of formula, it is P divided by S. Now let us look into this diagram. Over here, we have S, which is given by V into I. Here it is. Q component is given by Vi sin phi, and P component is given by Vi cos phi. Fine. So if I consider this, power factor will be P upon S. P is Vi cos phi, and apparent power is V into I. So your power factor will be cos phi. Now, power factor, ideally, we want it to be very, very close to 1. That means this angle phi, right? This angle has to be very, very close to 0 because we know that cos of 0 is 1. Whereas if we increase the degrees of this power angle, the cos factor, the cos phi will keep on reducing. So minimum value is power factor will be very, very close to 0, but the maximum we can get is 1. So it is always between 0 and 1 power factor. In this diagram, if we say that if we want to reduce the height, there is Q. If we want to reduce the reactive power Q, we have to reduce the height. That means we should have as small power angle as possible. That means phi should be very, very less so that your cos phi is maximized. Okay. So over here, if phi should be minimum, the Q should be very, very small. So Q will be very, very small if phi is small and cos phi will be close to 1. Okay. So in this experiment, we have to set up the RL circuit with 100 volts RMS, 50 hertz single phase AC supply, and R1 and L1 values are given to us. Here, if you see carefully, a coil has internal resistance here, as you can see over here. So that has been added to, for simplicity, added to R1. So the total R register in the circuit is including this internal resistance of the coil, because coil is also made up of, a material which will have a resistance. So the entire resistance is R1, which is 2069 ohms, and L1 is 5 hertz. And we need to measure the power factor of this circuit. Now, Let us set up this circuit in LT-SPICE, in Proteus, and let us observe what are the calculations. Okay, so let us start with the Proteus simulation. Okay, in Proteus simulation, we have to go to the components, and we have to first select resistor. So 0.6 metal film, you can select any one value over here and click on OK. Okay, so next we want to select the capacitor. So for selecting the capacitor, again we go over here and just type capacitor. Okay, so various types of capacitors will be available. You can click on this. The best one will be the polyester layer. Okay, so you can select this value and click on OK. Next is very important, inductor. You just type inductor over here and click on this, and you can select, I think the first value is fine. Yeah, the very first value you can select and click on OK. Fine, so all the three components are ready. Now we have to connect it. I mean, let me expand it for you all. Okay, so we have to connect the components one by one. So let us start connecting the register. So this is my register. I will expand this little bit so that it's visible. Next will be your inductor. So I'll place the inductor over here. Yeah, like this. And now we require the power source. That is, we require the 100 volts AC supply. So you go to generator, and from here select sign, and you can place it over here. Okay, and now you can double click on it and select it to sign, and you have to give frequency as 50 hertz, and RMS value you have to give it around 100. Okay, and click on OK. Here you can give the generator name as VS, like this. Now we can do the connections. Before doing the connections, we also require a milliammeter, AC milliammeter basically. So over here, what we need to do is, let me just push it a little that side, because we will require some more components over there. Okay, so I will require, you can go to this instruments, and we require a AC ammeter. Okay, because we want to measure the current. We can place the AC ammeter over here. Yeah, like this. And also we need to see what's the value of the AC, the voltage, whether it is 100 or not. So we can connect it like this over here, AC voltmeter. I hope that this connections are clear. I can place it over here like this. Okay, now I can join them together. Here I can join this together. Yeah, and also I need to push this a little further, because I need to connect a wattmeter also, a wattmeter to measure the power. So over here I have connected a wattmeter. Now the connections is as follows. So this terminal will go over here like this. This will be over here, and the remaining circuit you can connect it like this. Okay, so you can join the connections, and from here it will go over here. Fine, and this one you need to connect it over here. It's very close, but connect it carefully. Yeah, like this. So we have connected the wattmeter, we have connected the AC milliammeter, and connected the AC voltmeter. So you can double click on this and select on milliamperes, because the current measurement will be in milliamperes for this circuit. What is one thing missing is we have to set the values. So let me just go to view and a little bit zoom out and adjust this to screen now. So zoom to area. See that, please do it zoom to area, because it's visible very small when you upload it in the Google document. So go to place, and we want to select the ground. So go to terminals and click on ground. Okay, and we can join them with a wire. The circuit is almost complete. We can also label it. So place, we can go to text and we can add the text over here and we can write RLC parallel circuit. Okay. Basically it's a RL parallel circuit with a capacitor in parallel. So we are saying RLC parallel circuit. And here you can give it around 0.3 inches and click on OK. Okay. So actually it's power improvement circuit, not a problem. It's a power factor improvement circuit. So that we have to keep in mind. Now we have to change the resistor value. So over here, I'll double click on the resistor value. Okay, I'll have to right click over here and edit properties. And I have to give the value as 2069 and click on OK. And here, similarly, the inductor value has to be 5 Henry. So again, I have to right click over here and edit properties. And over here, I can just give 5. It will by default take it Henry, or I can give 5 Henry. Not a problem. So I've given here 5 Henry. Okay. And also the source over here, let me just check. Right click over here, edit properties. Yeah, it's 100 volts RMS value. And it's a VS source. It's a sinusoidal wave. And hertz is how much? It's the frequency. Let us check once. Yeah, the frequency is 50 hertz. Fine. So we have connected this circuit now. Now let's check with observation table what are the values. Okay. So for checking out, we need to click on the simulation play button and it will show you the values immediately. Yeah. So it's showing the values over here. Yeah, one more thing we need to take care is this is VA, right? So we need to stop the simulation. We need to right click. Okay, I need to stop the simulation. We need to double click on this and select as watt. Okay, which will give us the true power. So please do this step. Display range should be watt and click on OK. And now if you simulate the circuit, it will give us the current. The AC voltage is 100 volts RMS. So we have written here RL circuit. This is the RL circuit basically. Yeah. First of all, we are doing for RL circuit and then we'll go for RLC. So the voltage is practically its observed value is 100. The current is 38.8 milliamperes as it is visible over here. Value of P. Now, what is P over here? We have seen P is the true power. So true power over here is displayed as 3.07. Okay. And S, how will you calculate S? S will be V into I, that will be 100 into 38.8 milliamperes, that will come out to be 3.88. Fine. And the power factor, how will you calculate the power factor? Power factor will be P by S. So if you divide 3.07 divided by 3.88, you will get 0.7912 as the power factor. Fine. So this was the power factor. Now let us look into the calculation somewhat. So this is for the RL circuit. Next we'll do for the RLC circuit. Fine. Now I will, yeah. As soon as this is over, you can take the print screen of this and attach it in the Google document like this. It will look like this. Fine. So please add your name and your roll number additionally. And here below you can write your all the calculations if you wish to. Mainly the power factor you can write PS and power factor and the current. Fine. So next we'll look into the calculations of this. Okay, so let us concentrate on this now. Let me make it around 20% or so. Yeah, now it is visible. So Z will be, Z is the impedance. Total impedance will be R1 plus JXL1. Okay, so it will be 2069 plus J. XL is 2 pi FL. So 2 pi F is 50, L1 is 5 Henry. So that will be 1570.8 ohms. So if you use, you have to convert this rectangular coordinate into polar coordinates. So use polar bracket 2069 comma 1570.8 in the calculator, right? Directly write this in the calculator. You will get a polar coordinate. So the polar coordinate Z is 2597.72 and value it's this, and the degree is 37.206 degrees. Okay, so what is the power factor? Power factor will be cos phi. So cos of 37.206, which will be 0.7964. So that's the value which you are getting theoretically. So theoretical power factor is 0.7964 and practical we got it as 0.7912 for RL circuit. Now how will you calculate the current? Current will be V1. This is your V1, which is 100 upon Z. So that Z value is just 2597.72. And if you calculate in a calculator, 100 divided by this value will be 38.49 milliamperes and this degrees. So we are getting around theoretical value as of current as 38.495 and practically we got it as 38.8 milliamperes. How will you calculate S theoretically? V1 into I1. So 100 into this value, I1 38.495. So we get S as theoretically as 3.8495. Okay. How will you calculate P? P will be I1 square into R1. That will be 38.495 milliampere square divided by into 2069. Okay, this value. So you will get 3.0659. So P will be 0.3659, whereas in Proteus we got it practical value as three simulated value, actually we can say 3.07. Okay, so all the readings are coming quite accurate. Fine. The voltage, the current, the power, the active power, right? And we have the apparent power S coming very close, and the power factor also coming also close with the calculation, with the hand calculations. Now, next we take the observed values. So we simulated this RL circuit in Proteus over here like this, and we got the following values. V1 was 100, I1 was 38.8 milliamperes, P true power from the wattmeter directly we got over here like this 3.07 watts, and S1 was V1 into R1. Just multiply this, so you'll get 3.88. So from here cos phi will be P upon S, which will be 3.07 divided by 3.88, which comes out to be 0.791. Okay, so next what we do is we set up the RLC circuit with 100 volts RMS, 50 hertz, single phase, but we add a capacitor in parallel with this RL load. Okay, so first of all, we need to determine the value of C1. Now you will say the C1 is directly written. No, we want to improve the power factor. So let's say we want to make the power factor as 0.9. Earlier it was 0.79. We want to make it 0.9. So what is the value of C1? So we reverse calculate. So these are the theoretical calculations to improve the power factor parallel combination. That is, C is connected in parallel. We have other case also where C is connected in series with this RL load, but we are considering C1 to be in parallel. Over here from the previous calculations, we know Z value, the power factor value, and the power angle and I1 value were known to us. So over here, IR1 will be I1 into sine phi. So sine phi is sine of 37.2. That comes out to be, so IR1 comes out to be 23.458 milliamperes. Now, as we consider the capacitor to be the ideal one, so the active power of the circuit will remain the same in case of this. Okay, so PN, that is the new power, active power, will be equal to the earlier one. We got it as 3.0659 watts. Let us check. Yeah, so 3.0659. So the same active power will remain the same. So now we wish to improve the power factor. So let's say the new power factor is 0.9. So over here the power angle, the new power angle will be 25.84 degrees. So over here the new current flowing into the circuit will be Pn divided by the new active power divided by V1 into cos phi. Okay. So why V1 into cos phi? We can see over here. Yeah, this P. This is P upon S, right? So power factor will be this. Yeah. So the current will be the power, the P is actually VI cos phi, right? So I will be equal to Pn divided by V into cos phi. So that's why we have written this formula. So the new value of the current will be the new value of the active power, that is Pn divided by V1 into cos phi n. So that will be 3 Pn we calculated, remains the same. So it is 3.0659 and this is 100 into the new power factor, that is 0.9. So the new current which we get is reduced current, which is 34.065 milliamperes. So that's what we have written over here. Voltage is this, the new current theoretically is 34.065, and the P values remains the same as earlier, the active power remains the same. So your P is basically your active power or the true power. So the true power remains the same as the earlier case. Now we have to just calculate S. S will be 100 into, V into I, that is 100 into 34.06. So you see, the S value will be 3.406, and the new power factor theoretically will be wanted as 0.9. Now, let us proceed further. Now we have calculated the new current. Now, what is IR1 new? IR1 new will be IN times sin phi, which will be 34.06 milliamperes into sine of 25.84. This is the new value of IR1, which is 14.8475 milliamperes. So, what will be IC1 basically? Over here, the current through the capacitor in the circuit, it will be given by IR1, the earlier value, and IR1 new value. So this is what we get, 23.458 milliamperes minus 14.8475 milliamperes. So the collector, so the capacitor current will be right now will be 8.61 milliamperes. Actually, we are doing this calculation to find the unknown value of C1, because we want the power factor to be zero point 0.9. So we are reverse calculating the value of C1. Okay, so in the process, IC1 is 8.61 milliamperes. Now, what is XC1? Right, mod of XC1 will be V upon IC1. So V is 100 because it's a parallel voltage. Over here, we can see over here the voltage is in connected in parallel over here. Yeah. So over here, the XC1 will be 100 divided by 8.61 milliamperes. That will come out to be 11614.4 ohms. Okay, so that is the reactance offered by the capacitance. Now, what is C1 given by? C1 is given by 1 upon omega XC1. And what is omega? 2 pi f. So we substitute the values 1 divided by 2 pi into 50 into XC1, which is 11614.4. If you put these values in the calculator, you'll get the value of C1 as 0.274 microfarad. Okay, so 0.274 microfarad, that's the value we get. So we don't directly get it, we actually calculate it, right? And we connect this value C1 across the RL load, and that's how we get the power factor as 0.9. And as we have already calculated, I already said, it is V1 into I1, which is 3.4065 VA. Okay, so that's the reading which we have written over here, 3.406 VA. Okay, now we set this circuit in the Proteus and we check it out. What's the values we are getting? Okay, so we close the simulation and we go to components and we add the capacitor over here. Okay, so capacitor will be added in a parallel, so we can do the connections quickly. Remaining circuit we can connect it as it is. Yeah, so this is my circuit now. Now let's check the okay, the value of C has to be set. Okay, fine. So I can check over here, double click, I can put it as 0.274 microfarad. Okay, and click on OK. And now if I simulate, I may get a current and a voltage which is desired. Okay, fine. So what's my new values of the current now? Okay, fine. Let us check in the observation table. So the voltage remains the same. Even the active power remains the same. If you can see over here, 3.07, even after connecting the capacitor. Now, if you see over here, the current has reduced. Earlier it was 38.8. Now it has reduced to 34.2. This is the observed current, as you can see over here, right? And now how we can calculate S? S will be 100 into 34.2 milliamperes. That will be 3.42. And how will you calculate the power factor? Power factor will be P upon S. That will be 3.07 divided by 3.42. So as you can see, the denominator is reduced, so the power factor will increase. Okay, so power factor was given by P upon S, capital P upon capital S. So the denominator is reduced from 3.88 to 3.42. Hence, the power factor is increased to 0.897. We want it as 0.9, but we are getting as 0.897. That's quite an improvement over the circuit, right? So as you can see over here, the power factor is 3.07 divided by 3.42 in the calculator. That will be 0.897. So that's an improvement in the power factor. In the most circuit, we have seen that the current is getting reduced from 38.8 earlier in case of RL circuit, and after including the capacitor in parallel with the RL load, this current has reduced to 34.2 milliamperes. Okay, so that's the power of your power factor improvement. Now, in reality, in practice, this is just for the test case. In reality, the current is in amperes. So let's consider that if the current is around and the supply voltage is around 230 volts, right, 150 hertz. So this is just the numbers which we have taken to verify the concept, but the concept will be applicable whenever the current is in amperes only. Now let's consider a scenario that if you want to improve the power factor, the earlier current was 38.8 amperes. Let's consider this. And after the power factor improvement, the current has reduced to 34.2. So almost like 4.6 amperes of current you are saving. That means you're saving that much amount of power and the energy, right? So this normally this RL is the inductive load. It's basically an induction motor. RL load is an induction motor. So that's how we, I mean, it's the amount of power and energy it consumes. So basically, if the current requirement is less, that will save the power. So that's why we go for your power factor improvement circuits. I hope that this point is clear now, absolutely, right? With the power factor improvement, the current in the circuit has reduced. And if it is in the amperes, we are saving a lot of current and the power. Okay, so let's go to the observed value. So observed value, we already got it as 100. I1 is 34.2 milliamperes. P is 3.07 watts. S is V1 into I1, which is 3.42 VA. Okay, and the power factor is 0.897, which we got it. Okay, so for this circuit, what you all do is odd roll numbers. Whoever is odd roll numbers, take the value of R1 as 2150 ohms, L1 as 5.2 Henry, V1 is same 100 volts RMS, 50 hertz, and with those with the even roll numbers, right? The last digit is even roll number. So you calculate, you take R1 as 200 ohms, L1 as 4.8 Henry, and V1 as 100 volts RMS value and 50 hertz. So the sample calculations are given for you, right? You all can refer this calculations. Fine, and calculate and make this observation table, right? So include this all the readings in the Google document. So with the new values of R1 and L1, please complete this power factor improvement experiment. Okay, so that's it for EEE lab. I hope that you all will complete everything on time. Fine, so that's it for this lab. Next time we'll see another circuit in EEE lab. So okay, thank you for patient listening and have a good day.